Okay, so now that we're recording, welcome back. Hopefully you enjoyed your weekend. Hopefully you got outside to enjoy some of the beautiful weather. Did you? Did you? Or did you stay inside and do nothing but study? No, I know you didn't. I know you didn't. You got outside. Hopefully you got outside. It was absolutely gorgeous. What we want to do right now is take a quick look at problem set 2 to kind of identify any hiccups, any problems there that were lingering before we move on into the 1.3 and 1.4 stuff. So if you want to open up the problem set 2 document, I'm curious, what did people find interesting, fun, exciting, difficult? What kind of comments you got for me? I have background music, so I'm just jamming out. It's a Bach cantata, so it's not really jamming, but you know. Nothing? No comments? No questions? No stumpers?
One second.
Okay.
Let me find problem set 2. When we were doing number 6.
Number 6, okay.
C, number 6C,
Mhm.
regarding liquid and not salt.
Yeah.
Yeah,
I'm being tricky. That was a trick question.
It was, and I wasn't quite sure how to handle that one.
How about this? Answer me these two questions. How much liquid is flowing into the bucket at any given moment? What's the rate? Yeah, what's the rate of water or liquid flowing into the bucket?
A gallon per 2 minutes.
Okay, so a gallon every 2 minutes. So you could think of it as a half gallon a minute, right? Going in. How much is going out of the bucket?
It was the same thing, right? Yeah, 1 gallon every 2 minutes leaves the bucket. Yeah.
So therefore, how much liquid is there going to? How much change in liquid is there going to be in the bucket?
Every 10 minutes.
Think about it this way: inputs and outputs are the same rate.
Yeah.
So how much?
There's no change.
No change. There's no change in the amount of liquid in the bucket. But remember, that's not what our differential equation is all about. Our differential equation is all about the amount of salt in the bucket at any given time, the rate of change of salt, not the rate of change of liquid. So that question of, you know, what is the amount of liquid in the bucket after 10 minutes? Well, it's the same as it was at the beginning. It's going to be 5 gallons? Yeah, 5-gallon bucket because it starts full and it doesn't change. So that was me being a little sneaky.
I see.
I have a question about that because after a certain point, so much salt is in it that it's actually going to change. So were we to assume that the bucket was only 5 gallons and that was it?
Yeah.
Okay, we weren't to
so
assume
when
that
you
it's
say
bigger and then that it could, I mean, because theoretically it could have been bigger and just held 5 gallons.
True. You could think of it that way. One way of thinking about it is with salt, certainly in water. Water can hold a tremendous amount of salt before it starts to change volume.
Up, yeah.
But I mean, it would have to supersaturate in order to reach that point. And by the way, the concentrations that we're dealing with are nowhere near supersaturation. So good point. I actually verified this with a friend of mine who's a chemistry professor. So. And then he gets really nervous and he's like, why are you asking me this? I'm like, because I'm trying to set up a problem for my class. He's like, but you don't teach chemistry. What do you want to know? I'm like, you need to relax. God. I think he's just jealous. Okay, so number 6, setting it up, drawing a diagram, setting up the equation. Once you set up the equation, of course, it doesn't say anywhere on there that you need to solve it by hand. So hopefully you made use of Maple and just did desolve with an initial condition and got your equation for the amount of salt in the bucket at any given time. Or did you do it all by hand?
I did.
You did. Well, I mean, look at it this way. It didn't hurt. It gave you good practice. And of course, you can verify the solution with Maple, right? So even those moments on these problem sets or on exams where I say specifically, you must do this by hand, I am not saying, and you must never touch maple. Stay away from maple. No, 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 no. I just want you to prove that you know how to solve this equation using the analytic techniques that we've developed. But you can totally check it and make sure you get the right answer with maple. I hope you check it. It makes it so much easier for me to grade if you check it, right? So keep that in mind.
I have a little question.
Sure.
I couldn't get my picture. I put my picture in maple, which I've never done before, and it wouldn't. It was turned sideways, and I couldn't get it to rotate, so I just left it. So
That's
I was.
fine.
I
That's
mean, I
fine.
tried
Yeah.
editing the photo to turn it sideways, and it was a nightmare. So
Yeah,
I
it
just
turns
left
out
it.
that if you take your phone and then you do like a landscape photo, some phones, and I don't know why, some phones encode the image so that it is definitely that is the preferred orientation for the photo. Other phones don't. Other phones don't encode that, and so when it gets interpreted on a computer or on an application like Maple, Maple just goes, sure, I'll just show what you sent. And Maple does not have a very good photo manipulation or photo editing editor, right? So it's not very good at doing that. But yeah, it's not the end of the world. I can live with it. Anybody use the drawing tool in Maple to draw a sketch of their? It's not too bad. I mean, you can add words and arrows and stuff. It doesn't take very long. Some people like to draw by hand, and that's fine. Just, that's cool. Other questions? Anything else that came up on that problem set? There were 6 problems. It's a long problem set. How about the predator prey stuff? How'd that go? Did the reading help as predicted? Yes, no, maybe so. Okay. Well, every once in a while, there will be points when I'll say, you know what, they do a really nice job of laying this out in the text. Just read this paragraph or read this page. And I'm never going to assign you like, a chapter of reading or anything like that. It's always going to be like, here's an example I want you to check out in the book because they do a really nice job of it. So it only happens a couple of times, but the book is written to be read. And a lot of math textbooks are not written to be read. This is one that is definitely written to be read. And so I like the way they write some things every once in a while. The other thing that pops up occasionally is question number 3, the one about Alice, Bertrand, and Cassandra. Interestingly named A, B, and C to make it easy to keep them separate. I'm curious, first of all, what obvious equilibrium solution were they missing? Did you spot it? Did you spot it? Did you spot it before you were prompted with part B? I'm curious. Paul, what were you gonna say?
Y equals 1, I think.
Y equals 1. Because if you throw in y equals 1, it's in equilibrium. The dy dt is equal to 0. What about t equals -2? Is that an equilibrium solution? Matt, you're shaking your head. Why?
With that, would it just be undefined because it'd be something over 0?
Yeah, first of all, it would be undefined. It's not equal to 0, it's undefined. Second of all, remember, equilibrium solutions only occur when the dependent variable, when you plug it in, it sets the derivative equal to 0. So there's no equilibrium solution for an equation that's dy dt that you're going to sub in a value of t and make it equal to 0. That doesn't count as an equilibrium solution. It would only be if the dependent variable makes the derivative equal to 0. That's important. That's a key idea. So I'm curious. I haven't looked at any of the stuff that you've submitted for problem set 2, but in the past, when I ask questions like this, it's fairly common that students will immediately try to solve the differential equation. Like they'll do I'm going to find the general solution and then show that each one of the people either matches a specific version of the general solution or not. Did anybody try that and go that route? Solve the DE first? Let me phrase it this way. If I give you a differential equation and I say, hey, I think this is a solution to the differential equation, what's the most direct, straightforward method for proving whether it is or it isn't?
Plug it in both sides.
Yeah, literally substitute that into your differential equation and see if it makes a true statement. So, for example, I'm looking at um, the problem here, and so Alice says that y equals t squared plus 1 is a solution. So that means we should be able to take that value for y, t squared plus 1, and substitute it in on the left-hand side. So take the derivative with respect to t of t squared plus 1, and then we should be able to sub it in on the right-hand side. Plug it in for y, so t squared plus 1 minus 1 over t plus 2. And we should be able to show that both sides of that equation are equal to each other. If they're not, then what does that mean about Alice?
She's wrong.
She's wrong. Alice is wrong. And that's okay, but that's good to know that you can always substitute something into the differential equation to prove whether it is or it isn't a solution. That's kind of the most direct approach. Now, if you wanted to solve the differential equation, get the general solution, and then say, well, for certain values of the constant, this would be a solution, or this would be a solution, or this would be a solution. You can do it that way, but that's kind of taking the high road, if you want to think of it that way. It's a lot more effort in the sense of what's going on. Of course, you have Maple, so you could just say desolve and then have it kick out the solution and then prove whether that solution looks like Alice's, Bertrand's, or Cassandra's for specific values of the constant. So that's another way you could do it. Let's see. Yeah, those are the ones that I would identify as needing kind of little pokes once in a while. Any other questions on that before we flip the page? Lemonade, nothing better. Okay, so here's what we're going to do. We are going to, I'm going to close down problem set 2. And what we're going to do is turn our attention to classwork problems for 1.3 and 1.4. Now, I have it as on good authority, because I know the guy who runs the YouTube channel, that not everybody has watched the videos for 1.3 and 1.4. I don't know who, but there's not enough views to warrant everybody having watched them at this point. So if that's you, start off by apologizing to your teammates and saying, geez, I hope we can figure these out without me having done the notes yet, right? So be willing to work with your teammates. You're going to be working across 1.3 and 1.4. So you'll notice I've assigned some specific exercises. So Team Diff, Anthony's not with us today. Sorry, Tony, Chris, Bennett, whatever you want to call him. He's not with us today. He will be back, but he wrote me and said he can't be here today. And so that means, yeah, RIP, Chris. That means you guys are going to be doing section 1.3, exercise 5, and 1.4, exercise 2. And you can see the other two teams, Team Phi and Team Q. You can see which exercises you got assigned. So I'm going to turn you loose. We're going to split up into our breakout rooms. I just have to do the assigning process here. Manually, 3 rooms. Create the rooms. So this first one is going to be Paul, Wyatt, and Quentin. The second one is going to be Matthias, Stefan, and another word for bathroom, and breakout 3 is going to be the remainders. Okay, so I'm going to open up the rooms and have you guys go work on those. I'll give you a couple minutes. I'll pop in a minute or two to see how things are going. Hi, Quentin. Bye, Quentin.
I think he wants us to plot it though.
Yeah.
So we go
I'm baffled.
D plot.
Isn't I of t just the 3 different constants?
Yeah, that's what I'm working on, but I can't figure out how to graph it with that, how to plot it without having 3 variables in there.
Well, you could you could just refer to it as you could just give it another name, call it another parameter name, and remember to put a multiplication after the parentheses there.
Oh, right here.
Yeah. And then call it, P or whatever. And then you can change the value of P and rerun that desolve. So because they're only going to be constants in this particular problem. Yeah. And so I think, if I'm not mistaken, yeah, your differential equation is not in terms of I of t over t. It's d theta of t over t.
Oh, d theta. Okay.
That's why it's giving you the error.
That's why it's giving me
Yeah. It's like, oh, okay, yeah, I'll take the derivative of something with respect to t, and then the other side doesn't have it. So, oh, nope. You just want that inside those parentheses to be theta of t. So you've already got the diff. So that's already doing the derivative. Nope, not over dt. Just theta of t.
Oh, theta of t.
Yeah, you got to write it as a function, and then get rid of the denominator there.
I gotta change the rest.
And you're missing, your parentheses. So it's diff open parentheses, theta of t, comma t, and then close parentheses. So you've got an extra close right where your cursor was.
Right here.
Yep.
Oh, wait.
Nope. No, you don't want another one. You want to get rid of one.
Okay, I'll look at it.
Delete one more time.
And then also you gotta change the rest of the thetas in there to theta of t.
Yep. So it recognizes them as functions.
Cosine theta of t then.
Theta of t. Yep. Now give it a whirl and see how you get. Hey, look at that.
That looks like fun.
Yeah. Nobody said it was going to be pretty, but of course, Maple can't do anything more than that until you specify a value for P. And fortunately for us, our values of P are pretty fixed. So, so I'm going to pop out and see. So you guys are doing number 5 for 1.4, or no, 1.3. And then which one are you doing on for 1.4?
Hang on. What do we got? I think it was number 2.
Okay. So one of you can start working on that one if you're
Right.
cool with giving it a go, and then you can double check it with each other. So
Okay.
I'll let you guys keep plugging away. I'm going to go hop in one of the other rooms here.
Okay. Perform Euler's method with the gift.
It's there's no t in the equation.
Yeah.
That's my thought. He just joins. Maybe we can ask him.
Hey,
Hey, how's it going?
pretty good. What you guys looking at?
What's an autonomous differential equation?
Autonomous. That's one of those terms that came up in, actually, we've come across it before, and it also came up again in 1.3. Autonomous means the right-hand side is only in terms of the dependent variable.
Okay. So like the baseball example.
Yeah, exactly. Or if you're looking at the 1.3 classwork, question number 3 is an autonomous differential equation because it's dy dt equals some function of only y. So that means whatever's on the right-hand side, it's only got y's in it. It doesn't have any t's in it. So that's what makes it autonomous.
So in terms of slope fields, do they always kind of converge to the same general location like the gravity one did?
That's a good question. I would suggest, just like on the problem set that you're going to be doing for this, try a bunch of different, just make them wildly different slope fields. Make the DE plot for a whole bunch of different autonomous differential equations, and all three of you can do it, and then kind of share your screens and compare and say, what do they all have in common? What do the slope fields look like? And I think you're onto something if you're comparing it to the baseball equation, but I don't want to spoil the ending, so I'll let you guys play around with it a little bit. So yay, give it a shot. You've got the powerful tool of Maple that you can try a whole bunch of different autonomous differential equations. You can make them polynomials, you can make them sinusoidal, you can do whatever you want and see what happens. Cool.
It's bueno.
And what number are you working on for 1.4?
One.
Yeah.
Number 1, okay. So that's yeah, okay. Yeah, it's okay. That's actually I tried to make one of the questions be a little tricky and one of them be a little bit easier, and so that one I think you'll find it a little bit easier. So, yay. Okay, I'm gonna let you work on that. I'm gonna go join room number 3.
Sounds good.
Toodaloo.
It's not quite.
Did he have you add the curves too? Yeah. And describe
Which
behavior.
one? So good. How you know sketch both.
Okay, here, let me show you.
With at least 3 different solutions on each. Oh,
How's it going?
it's going.
Yeah,
Starting through Maple here.
that's cool. Which one are you on? You
We're
working on?
on 1.3, problem 1.
Problem 1.
Can
Okay,
you see
that's
this?
cool. Yeah, it's beautiful.
Okay.
That looks good to me.
Yeah, does this look like the left one to you guys?
Yep.
Okay, awesome.
Yep. Well, yeah. So
Is it?
Definitely.
Yeah. Yeah, because
the second one's pretty similar, but it's not quite this. Yeah, that's correct.
Okay, awesome.
So what are the what's the word I'm looking for? What are the important features of this DE plot that you can kind of hone in on and verify?
I would definitely say the horizontal line at 1.
Yeah, that's what we would call an equilibrium solution, right?
Right.
As t gets bigger and bigger, all the curves seem to head towards y equals 1. And the other thing to keep in mind is the arrows on either hand. Let me turn on my video so I can point and you can see what I'm talking about. But the arrows seem to be pointing towards, y equals 1, right? So the solution curves are going to be heading like that. But they don't have to. So if you look at y equals 0, you can see everything is headed kind of away from y equals 0. So that's a totally different situation. That's not the same kind of equilibrium solution. Everything doesn't head towards it. Everything's heading away from it, right? So equilibrium solutions are really important to notice about the graphs or the slope fields. The direction of the arrows in particular regions, right? The kind of slopes that you see in those regions. Those are super important. And the other thing that pops up when we're talking about kind of definitions for this stuff is the slope field, that you're seeing right now is an example of an autonomous differential equation. What makes it autonomous?
It's the only one variable on the right-hand side.
Yeah, not only one variable, but which variable is it?
I can never remember if it's...
Is it the dependent?
The top of the differential, right? The dy, the dependent variables on top. And so an autonomous differential equation is defined as being only a function of the dependent variable. Right. So if you're looking, by the way, if you're looking at number 3 on the problem set or the classwork, 1.3, number 3, it says dy dt equals some function of y. That is the textbook definition of an autonomous differential equation. Right. So what you're seeing right now is an autonomous differential equation and its slope field. And the question is for another group, but a question is, are all autonomous differential equations, do they all have some characteristics in common? And the answer is, yeah, you can see them when you plot their slope fields. So for example, the other slope field that you're supposed to match to an equation is not an autonomous differential equation. And I'll let you ponder why that might be and when you figure out which one it is.
For part B, are we
Mhm.
just plugging in like random initial conditions basically?
Yep. Just make sure
Alright.
that they're distinct, right? So you don't want to plug in initial condition values that are on the same solution curve, right? So I would
Okay.
say y of 0 equals one number, y of 0 equals another number, y of 0 equals another number,
Okay.
and you'll get
Okay.
three solution curves.
Just to clarify
Sure.
on the basically the syntax of like how it's laid out in Maple.
Yep.
When we're adding our initial condition, it has to go in between the x and the y in terms of the domains.
The independent and the dependent. Yeah, for the ones that we're doing right now, I don't think it does, but later on it will matter. So I
Okay.
tell everybody, yeah, just get used to doing it this way.
Okay.
Because when we do it we're going to be messing around with systems of differential equations,
Mhm.
and then it does matter.
Okay.
So yeah, the way Hannah's doing it is perfect, and she just got an error that is exactly the same error as is in the notes. One of the things that I talk about in the notes.
Oh,
It's a huge honking mess of an error, but it's something really simple. You're missing one punctuation mark.
oh, it's a comma. It's a comma.
You see
There
it?
it is.
There it is.
Oh.
Ta-da!
There we go.
There you go. So it just so happens that you have two solution curves on the graph, but notice one of your initial conditions is not showing up. And I'll let you think about which one it is and why it's probably not on the graph.
For part C, it says describe the behavior of the solution of y, so the initial condition at 1/2.
Mhm.
Can't we just make that one of our three that we plug in?
You certainly could, but then
Okay.
the word describe means showing me a graph doesn't cut the mustard. Describe,
Right.
explain, these all require
Right.
English, right?
Okay.
No, that's okay. This is learning how to communicate with me, right? Because I'm going to ask you to do a lot of describing and explaining, and some people are used to just saying, "Well, here's the graph," but that doesn't describe or explain. You need to actually explain what's going on, what's happening to the curve.
Okay.
But yeah, you're absolutely right. You could make that one of your initial conditions.
Okay. And is that for each one? Like you want to know that for each
Yeah,
plot?
for both of your
Okay.
differential equations. Yep.
Okay.
Well, cool. So you're on track. Woohoo! I'm gonna go stop in one of the other rooms and harass them for a little bit. Boo.
What am I doing wrong here?
Let's see. You've got your dependent variable range, but you're not telling it your independent variable range. Or sorry, the
Oh,
other way
yeah.
around. The other way around. You've got your independent variable range, but then after your initial conditions, it should say comma, and then theta goes from whatever to whatever.
Like that.
Yeah. Oh, what's it like?
Oh,
Error
should I have
messages.
T on that side too? The T.
No, you don't need the T. Although, what's it saying? The number option must be specified before initial conditions. No, it doesn't. Equation. DE plot. You got your equation that you've defined. Have you defined it up above? Okay, yeah. Colon equals, yeah. So you did that. Oh, keep in mind you've got a parameter in your equation. So Maple runs into the P and it doesn't know what to do with it. So you'll have to change the value of P in EQ in order for Maple to be able to do a DE plot. The other possibility is if you leave the code just as it is and then right click on the code, one of the options down below is explore.
Okay, got it.
I'm gonna show everybody this later on today, and what you're now gonna do is basically it's like you're creating a slider bar situation. So I want you to skip EQ. You don't want that to have a slider bar. So put a little check box or check mark in the box in front of EQ, and put a checkbox in front of T, but you're going to leave theta. And so you're going to have theta go between values of whatever you want to whatever you want. And so this is like being able to, oh no, wait a minute. It should be P is one of the options. Why is it? That's weird. That's weird. Huh. It's apparently it doesn't like doing explore with a named equation in there. If you were to copy and paste the equation with P, you could do this process over again. And then, so you could do that instead of EQ in your code, just copy and paste the differential equation from up above.
Okay.
Or alternatively, you can just put a number in for P and then do your DE plot.
Okay, I'll just do that.
Yeah. And I think the numbers that it asks you to use are -0.1, 0, and 0.1. So might as well just use those rather than 5. Now remember, Maple won't remember that that's your equation until you hit enter after naming it, right? And now it remembers what it is. And that extra line, it's just extra. But now if you do DE plot, why is it giving you number option? That's really weird.
Number
your,
option. What is that?
okay. Don't know.
Hmm.
You've got your open brackets, close brackets. T is going from -10 to 10. Must be specified before the initial conditions. No, it doesn't need to be. D plot. That's really weird. I don't know why it's giving you that error. I truly don't.
Okay, well, at least I don't feel so bad then.
No, I mean, the problem sometimes that we run into with Maple is kind of doing code within code. It can sometimes get a little goopy. So one possibility would be to rerun the entire page, do the 3 exclamation points, and just rerun it from scratch and see if you get the same error. And then the other possibility would be, ow, sorry, my knee. One other possibility would be to just go skip down a line and retype the code. Just retype it as it appears. It's tedious, but there could be something as simple as like an extra space that shouldn't be there, or and sometimes our eyes don't catch it. But in retyping the code, that those problems go away.
Okay, I'll try that.
Yeah, sorry, I wish I could spot it. Sometimes these errors are not so clear. Let me do that. I'm gonna open up Maple and see if I can reproduce the problem that you're having. I think you're in text mode there. Yeah.
I mean, does that theta have to be theta of t at the end or no?
No, it doesn't. For stating the range, you're basically telling the graph what to name this axis and what to name this axis. So you can name it whatever you want, but yeah, you'd want it to be the same thing. Weird.
Okay, now that's really. Oh no.
Okay, there we go. Whew. Yeah. Sometimes errors start to compound and you don't even realize you're doing the same thing over and over, and you're like, why won't the machine do what I tell it to? So for you two guys, while you're waiting for him working on this, my advice would be hop over to the 1.4 problem and take a look at that. Have you started working on it?
That's what I've been working on right now.
Okay.
Here, I'll share screen.
Sure, go right ahead. I think he needs to relinquish in order for you
Oh,
to do
sorry.
that. Oh no, maybe not. I don't know. I don't know what the settings are that I have right now. So let's see what you got. Cool. So you got your with student numerical analysis. Let me make this full screen so I can see what's going on here. And then you're doing Euler. Got your differential equation, your initial condition, and where you want to go to. So the t equals 0.025.
Yeah.
That's telling Maple, I want to go to a t value of 0.025, and you want to do
Oh.
it in one step. I don't think that's what you intend. I think what you intend to do is to have a step size of
Oh, so
0.025. Is that
I
correct?
got it backwards then. So num steps would be the 0.025 because that's like the size of the steps.
No, num steps is literally number of steps. So you'll notice that for the one that you're working on, which is that one, I don't actually tell you how many steps to take.
Okay.
I tell you where you start. You start at a t-value of 0, and you go to a t-value of 1, and the step size is 0.025. So you got to figure out how many of those 0.025s are there in that interval.
Okay, hang on. I could just calculate.
It's just, yeah,
Or something.
it's just a quick calculation.
So 40.
That makes sense because it's a tenth of a quarter, right? So, 40 steps. And so, of course, Maple's not going to show you all 40 steps unless you force it to.
Right.
And of course, you don't have to see the entire table.
Mhm.
You could take a look at a plot.
Mhm.
You could take a look, if you don't do output at all, you just end it after num steps 40, it'll give you the approximated value. But the nice thing about the table is you get the approximated value as well as the right answer, Maple's numeric solution, right? So the only other piece of code that you may want to consider playing around with is digits equals. And so if you throw digits, comma, digits equals 6 or 10 or however many digits you want, it's literally significant figures.
Oh, did I spell that wrong? Yeah, I probably did.
Digits. Didgets.
There we go.
So notice it's added one more digit. And so you can see that the Maple's numeric solution is different than the Euler solution for those first couple of steps. And do you remember how to get it to expand the entire table?
I can't remember what it was.
I think if you double click on the table.
Oh, okay. So it comes up and it'll give me a giant. Okay.
Yeah.
Browse
And so you
matrix.
can, if you scroll down, you can see the Maple numeric solution is 0.97592, and the Euler's method solution is 0.97590. So they're actually really close. It's a really small error. But if you go out more digits, you'll see, well, maybe it's not that close after all. Maybe there's some rounding error that plays into effect.
I gave it the command to go only out to 40 spaces. Why did it go out to 42?
If you scroll up to the top, you'll see that the first two spaces are reserved for basically the title of, and the first step is actually the 0th step, if you want to think of it that way.
Okay.
Yep.
All right.
So that's one way to do it. The other way to do it, I think, is if you have your cursor on there off to the side. I think it's show all. Yeah, on the palette on the right-hand side context menu, it says show all.
Yeah, hang on. I got to push you guys. Yeah.
No, it's okay. I can see it. It's right there.
No, the thing. There we go. Okay. Show all.
At the bottom.
Yeah, and basically
Holy
it's going
crap.
to creates another table in the Maple document, right? So if you need to see all the steps, they're there. There's two ways to get it. One is to double click, and that opens up a separate window. And then there's the show all move. That's pretty handy too. So, okay, I'll leave you guys to it. You keep working. How's it going, Paul? Did you figure it out? Paul's buried in thought. How about you, Quentin? What's up?
I've just been helping kind of both of them right now, or mostly Paul, but just trying to do each of them.
Cool. How's it going, Paul? Did you figure it out?
I was muted. Yeah, I've almost got it figured out. We'll see if it turns out.
Awesome. Cool. I'll let you guys keep working. We'll probably get back together about 7 o'clock, a little bit before 7. So just as metering your time here. If you run out of stuff to work on, you can take a look at the next problem set, which is due on Wednesday. So,
Okay.
so I'm going to hop into room number 2. See ya.
Solution with y 0 equals 2. Sketch it.
Hey, everybody. How you
Welcome
doing?
back. We've gotten to part 2 of our second of 3 questions.
Cool. So wait a minute. So
That's what we've done.
part 2 of which one are you working on?
Number 3.
3. Yeah, so right now we're on 3B.
Oh, so 1.33.
Yep.
Yeah.
B.
Got it.
Yes.
1.33B. Got it.
Mhm.
Cool. So what did you think? How much of the slope field can you sketch from that information?
Everything above the t-axis.
Because the particular solution doesn't show us what's going on below the t-axis. Technically, we don't know what's going on after the curve reaches the top of the graph. But everywhere that you see a curve, all the way across, you can graph the slope field.
And that's because it's autonomous, correct?
Because it's autonomous. That means that if you look horizontally, everywhere is going to have the same slope horizontally. So for example, at 0,3, you say the slope is negative and it's like this. That means everywhere at a y coordinate of 3, they all have the same slope everywhere.
Okay.
So the curves are basically the same curve, just shifted horizontally.
Okay.
Cool, cool. Let you guys work on that. And what's your problem number for section 1.4?
Number 1.
Number 1. Okay. So give part B a look-see and give it like 2-3 minutes. If you're still working on it, set it aside. I want you to work on 1.4 as well.
Okay.
Okay. Cool.
Bueno.
Bueno.
Well, there's no x in the equation, so that's not
All
anything
right.
to worry about.
Here we go. I'm gonna share it. Come on over to my side of the screen.
Oh, very nice.
Ooh, nicely done.
Yep.
A quick shot with your phone. Very cool.
Sent to myself from Facebook from myself.
Wow. So somewhere there's a satellite. There's like, seriously?
Yeah, exactly. They're like, really?
Okay. But
I
that's why we
guess.
love technology. So.
That's right.
Oh. Oh yeah. Okay. Yep.
But I still need to find the new coordinates, technically, or rewrite it.
Yeah. Okay.
So x new is x old plus a half in this case.
So for you're doing number
yeah, half.
3A. Is that what you're working on?
Yes.
Mm-hmm.
So for that one, how many steps are you going to take?
Oh, 2.
How can you tell?
I'm just going off of the 0. The 0 is less than t, and t is less than 2.
Okay, so that tells us
could
how
be
far
wrong.
along the t-axis we're going to go. But you could take any number of steps to cover that distance.
All right.
So how do we know how many
We've got our
steps
change
to
of t
take?
is the 0.5, right? So
So
4.
it would be
1,
4.
2, 3, 4.
So for
Yep.
these problems, I actually don't tell you num steps. So if you were going to do this in Maple, which by the way, why wouldn't you? If you're going to do this in Maple, it's not that many calculations, so it's not that big a deal to do this, by hand. But if you're going to do this in Maple, Maple doesn't care what the step size is. Maple says, I'll figure out the step size. Just tell me where you want me to start, where you want me to stop, and how many steps to take. So num steps is important for Maple. But sometimes you're not given that information. You have to do a quick calculation to figure it out.
So you don't care if we use Maple, if we just go ahead and just plug it into Maple. You want me to show you every step?
No, I'm totally cool with you using Maple. And for these problems, notice, all I'm saying is perform Euler's method. And you can do that in Maple and have the output, right? But if I ask you for more information, like what do you notice happening to the error as you take more and more steps, right?
All right.
Maple's output actually, if you do output information, that'll actually show you the error for each one of the steps. And so that's handy to have. But if you just do the Euler's method with no output in, on there, and it'll just spit out after this many steps, the answer is this. The approximation is this. So my advice would be try it. You can do these by hand. There's only 4 calculations, so it's not that hard. But you can check your work by doing Maple, right? Pretty
Okay.
handy. Now, there'll be some later on, like number 2A. Notice it's going from 0 to 1, but take a look at the step size.
Oh.
Ugh. So that means, and the other group I was just talking to, they were like, so wait a minute, that would be like 40 steps. I'm like, yeah, you're not going to do that by hand. No. But once you start using Maple, you realize there's questions of how many digits do you use, because rounding error becomes a problem. So you have to be able to account for more digits. Because if you don't, then it looks like, oh, what do you know? The Euler's method solution is exactly the right answer. Well, to 4 decimal places maybe, but to 6 or 8 decimal places, it's not.
Right.
So rounding matters. So cool. I'll let you guys keep working on that. And are you all set with the 1.3 problem?
I think so.
Yes.
Comfortable with that? Okay, cool. So any other questions about 1.3 problem or the 1.4 setup?
How much more time do we have?
Maybe like 5-6 minutes.
Okay.
Okay, give you some time.
Thank you.
Yes. Man, apologies. This recording has been going this whole time. I forgot again to hit stop. So I'm going to hit stop.